Okay, so today is the last topic, okay, of this course, the Schrödinger equation. So this is what is in the book, okay. We won't have time actually to cover, okay, all these topics, and essentially I will talk today of this part, the Schrödinger equation in one dimension, okay, and this is very formal, and I will make some consideration on these equations and why it is so important in quantum mechanics and what we can do with its study. Okay, so what we saw last time is that De Broglie, he made some postulates. He said that in the same way that you can study the behavior of waves as if they were particles, okay, light particularly, okay. So you could associate a wave to a material particle, okay. So your particle is characterized by its linear momentum p and its energy E, and to this particle, okay, characterized by these two parameters, you can associate a wave which is characterized by its wavelength and its frequency. Okay, here I wrote F, I think, but after that I am using the Greek letter nu. Okay, so this is the wavelength lambda, the frequency nu. Okay, and so these two behaviors, the wave one and the particle one, they are related through these two expressions. Okay, and actually they are related through the Planck's constant h. Okay, so lambda is equal to h over p, and nu is equal to e over h. Okay, and so we saw the implications that these postulates could have on the observation of some behaviors of material particles, and we saw that it was experimentally evidenced, okay, that electrons, for example, they exhibit this kind of behavior, okay, if this lambda here, I'm going to call it lambda De Broglie, okay, this is a material particle, and so this lambda, as soon as it is possible to observe behaviors for this kind of lambda, interferences and diffraction, for example, so it cannot be too small, because if it's too small, you won't have the possibility to find a physical equipment, a physical arrangement to put it to evidence this behavior. So we saw that it was evidence through diffraction of electronic waves, which had a wavelength on the order of 10 to the minus meter. Okay, so you can, if it's much smaller than this, you won't be able to observe. Okay, and so it was observed through diffraction of these waves by crystals, okay, nickel crystals, particularly where you have families of atomic planes which are separated by this kind of distances, okay, angstrom, 10 to the minus 10 meters, okay. Smaller than that, you arrive at the dimension intra-atomic, okay, so this is much difficult to observe. And so so this was last topic, and we had some insight into how we can describe a particle which is localized. It has a position it has. Okay, we can say that this particle is around this position x, for example, in 1D. And so we could build a wave associated to this localized particle by summing a lot of waves with different wavelengths and frequencies. So it is possible to have some wave packet. Okay, so I can draw here. This is some wave packet. Okay, so this is the position x, and so you can you can build something like that. Okay, where your particle will be localized inside with this wave packet. Okay. On the other hand, we have something which is not very physical, but that we can describe as a free particle. Okay, the free particle has a constant linear momentum because we are going to speak about classical particles. Okay, they are classical mechanically speaking. They are not relativistic. Okay, and so you have the first law of the second law of Newton, that the forces applied to your system, okay, they are equal to the variation rate of the linear momentum, okay? And so if you have no force, okay, you have a free particle, no forces applied, so you will have a constant linear momentum, okay? And so if you have a constant P, it is well determined, you will have a constant wavelength, okay, also very well determined. And so we associate to this free particle an harmonic wave, okay, a harmonic wave. It has here a wavelength lambda and a frequency nu, okay, and so in this case we have chosen this psi is proportional to the sine of this phase x over lambda minus nu t. Okay, you can also write it like this: k x minus omega t. Okay, where k is equal to 2 pi over lambda and omega is equal to 2 pi times the frequency. Okay, so the question here is to be able to describe the behavior and to extract information on a particle, okay, based on this formalism, the wave, wave formalism, okay. And so what we are going to do, okay, we are not going to deduce this equation. It exists, okay, this equation that governs the behavior of these waves. This is the Schrödinger equation. So you are probably already familiar with things like, let me put a new page here. You have some equations, okay, for the movement. So you have the, let's see here. Okay, so what in mechanics, okay, the classical mechanics, okay, you have classical mechanics, you have Newton, okay, Newton law, and so this law is that F is equal to Tp over dt. This is the more general shape of this equation, and this is in the classical case m t2x over dt2, okay, in one dimension, okay. And so this is the movement equation. So you use it to describe everything you can describe on the particle, okay, its movement, okay. You have, in the case of electromagnetic waves, you have Maxwell equation, okay, Maxwell equation, okay, and particularly you can describe the wave equation. So the Maxwell equation, you have 4 Maxwell equation, okay? And from this equation you can deduce the wave equation, which relates, okay, the derivative of, here I can write, this is an electromagnetic wave, I can write the electromagnetic field, for example, Ax, Ey, for example, okay, over dz, dOis. Okay, this is a component of your electromagnetic field, okay, polarized in the y direction. This is the propagation direction, and this is proportional to the second derivative, really in relation to the time, okay, and the quantity between these two is, I have to think a little. Here you have volt per meter. Per meter, and so you will have volt per meter. Okay, this is y per meter square actually. D2, and so this is 1 over C2, yeah. Right. Okay, so this is the wave equation for electromagnetic waves. And so these two derivatives, they are the spatial one and the temporal one, and related through the velocity of propagation, okay? And so we are going to find an equation that describe, okay, we already spoke about the wave equation, okay, matter waves. We will call them psi, okay, of x and t in 1D. Okay, and so we want an equation that will describe these changes, okay, the evolution of this wave function, okay, as a function of the position x and as a function of the time t, okay. So a few things we can use to try to deduce, okay. I'm going to deduce it. It won't be very rigorous, okay. So it has to be consistent with the de Broglie postulate, okay, these two relations between the wave and the particle behaviors. It has to be consistent with the fact that the energy of the particle, okay, has two contributions. This one is the kinetic energy. I wrote it as a function of P, okay, we can also write it like that. Okay, this is the kinetic energy plus the potential energy, okay? And it has to be linear in the wave function because it has to obey the principle of superposition. How do I know that? It is because we have observed experimentally that it exhibits some wave behavior, and it is able to have superposition. It is able to interfere, okay, to have the diffraction, for example, by crystals, okay, is the result of interferences, okay, between waves. And so it means that the waves resulting from superposition of various waves, okay, which have to be solutions of the wave equation, the linear combination of these solutions is also a solution, and we observe, okay, this experimentally. So apparently we can use this principle of superposition, and to have the principle of superposition, the equation describing the evolution of psi has to be linear. Okay, we will see what it means. Linear in psi means that you cannot have constant terms. Okay, in the equation you cannot have terms proportional to powers of psi or of its derivative. Okay, And so this is one assumption, okay? And also we have to, in the case of a free particle, okay, when you have no forces, so you have a constant potential energy, I will call it V naught, okay? So this is no more a function of the position or of time, okay? This is a constant. So we agree that the solution should be of the shape psi of the position in time is proportional to some harmonic function of the position and time, okay, for a free particle. So we have some limit cases, okay, where we can find, okay, what we know, okay. So we have some ground to build this equation, okay. So if we use the first and the second conditions here, the first and the second, they are that it has to be consistent with the Bragg postulate and also with this way of computing the energy as a sum of the kinetic and potential energies, okay? So I will write it. What is it? This is E, the energy. This is P squared over 2m plus V, okay? So I have E equal to h nu, and I have P equal to h over lambda, and also...
Teacher?
Sorry?
This claim of the subject is no longer appearing to me. It might be some connection error, I guess.
You don't see the slides?
Yes.
Oh. So let me stop. Okay. So I was saying that, okay. So to obey, we are going to build, okay, this equation. And so I will begin with these two conditions. It has to be consistent with the Bragg postulate, and it has to be consistent with this way of building of computing the energy as a sum of the kinetic and the potential energies, okay? So here, E, the energy, is equal to P squared over 2m. So P is equal to h over lambda. We also can write it as h bar k, okay? Where h bar, oh, I wrote it, no. H bar is equal to h over 2 pi, and k is equal to 2 pi over lambda, okay? So we can write it this way. So P squared will be h bar square k square over 2m plus a potential energy, okay? So this one, we have no way of writing it in a general way because it will depend on your problem, okay? So something we can remember, if we want some wave equation, we want to have a relationship between the spatial and the temporal variation of this wave function, okay? And so we remember when we have the wave function for the free particle, okay, this is a harmonic wave sine of kx minus omega t. If you derive once as a function of time, it will be proportional to omega, okay? So this will be omega cosine of the phase, okay? If you derive, oh, this is not t here, this is x, okay? Why do I derive only one time here? Because I have here omega, okay? And I have k squared, and this k squared appears when I derive twice as a function of the position x, okay? And so I can say that I can try, okay, to see if this omega here could be proportional to the first derivative as a function of time, and this k square as the second derivative as a function of position, okay? And so I write it here, and I will put some coefficients. So alpha, okay, twice actually y, because we have k square, okay, plus v. Why do I multiply v by psi? It is because we saw, okay, this is the condition of linearity, okay, it has to be linear, okay, and so if you have some term here not proportional to psi, it won't be linear, okay, and so we have to have this derivative plus v times psi equal to another coefficient, beta, times the partial derivative of psi over t, okay? And so the problem here is to test this function to see if with that we can obey the other constraints, okay? And so we have to determine also what would be these coefficients alpha and beta, okay? So we come back to our free particle. We are going to do everything with the free particle, and to somehow generalize, okay? We won't demonstrate, we won't prove that it works for something else than a free particle, but I will tell you that it works, okay? And so we are going to do this only to have some physical insight in how this wave function can be, wave equation, sorry, can be built, okay? So I use again, okay, this wave, okay, a harmonic wave that I think that maybe a free particle will have, okay? I have no proof, okay? I can say for sure that it is this one, but it may be this one because it has a very definite and constant wave, linear momentum, etc. Okay, so I derive once with time, and I will have this expression. I derive once with position and twice with position, and so I will put it back, okay, in my trial equation here. So I will have alpha times twice this okay, derivative plus v times this function equal to beta times this derivative. Okay, so let's try to see if it works. And so on the left side of the equal sign, we have this one. Okay, so I didn't write it, but everything that is here is kx minus omega t, kx minus omega t, and here also. Okay, and so we will obtain this one, and actually it is not very agreeable, because on this side you have a sum of sines, so you have sine of kx minus omega t times minus alpha k squared plus v0, okay, and it should be equal to some constant here times the cosine. So how can you have some sine equal, okay, to a cosine? So this would correspond to very specific conditions, and so it doesn't seem to be the way to go, okay? So how can we do that? We obtained this because we said that probably the free particle would have this shape, okay? And so you see, what is the problem? It is that if you derive once here, you will have, from the sine, you will go to a cosine, and when you derive twice, you will have your sine back, okay? So you have this switch between sine and cosine functions. So what we can try is to say that the very function here, the wave function, is actually the composition of a cosine and a sine. So when we derive this function, we will have both, and we can see if it works, okay, if we have something more physical, okay? And so what you are going to do here you have a sum, but you have to put some coefficients. So I will have here the cosine of this phase, and here I will put some constant, okay, I will call it gamma, okay, which is a constant. And so now I have three constants, alpha, beta, gamma, okay? And so you do, again, okay, the derivative of this function, first as a function of time, after that as a function of space, okay, okay, so this is the same thing here, okay? And so once you have written this one, okay, you derive once, twice, you put it back in your equation, this equation here, okay? Maybe I can repeat this equation because it is okay, it would be nice to have it here. I will put it here in the corner, okay, to remember. So this is the equation, oops, some alpha missing here, okay? And so alpha times twice times this derivative, okay? So you write it here, and so you have this new expression. And so what you can do here is to group from the cosines, okay, on one side, and on the other side the sine, okay, terms. And so when you do that, you have the cosine times this factor, and here you have the sine times this factor, and this is equal to 0. So this is much better, okay, because now you will have two equations. And so for this equation have a chance to be true, okay, only if this one is equal to 0 and this term also is equal to 0, okay? Otherwise it won't be very general, okay? So we write that this term is 0, okay? And that this term is 0 as well, okay? So here we have minus alpha k squared plus v0 equal to minus beta omega gamma. And here we have gamma. I put it on the other side. The same alpha k squared plus v0 is equal to beta omega over gamma. And so it is possible only if gamma squared is equal to minus 1. Okay, so this may be seem very strange, but actually this only means that the solution, if we want in this shape, okay, with gamma, this coefficient of the wave function, okay, the coefficient gamma has to be plus or minus I, where I is the square root of minus 1. Okay, so this is a complex number, and so it will impose, okay, this fact on the wave function, okay, that it is a complex function of x and t. Okay, and so this is something very special. But before going on, I want to say something. You remember last lecture when we said that what was waving, okay, in this wave associated with a material particle was some wave function psi, okay, and we gave it some physical signification, okay, through its modulus square, okay. So the wave function doesn't have, okay, a direct physical meaning, okay, and this is confirmed here by the fact that actually this psi function, this wave function, is complex, okay. So in the real world, meaning, okay, the world we live in, okay, with these particles, okay, existing particles and things like that, okay, what we can measure, okay, to characterize the behavior of a particle, okay, we can measure real, okay, in the mathematical sense, okay, real quantities, okay? So psi being a complex function, okay, we understand that it has no direct physical meaning, okay? But when you put here psi square, okay, it is real, okay? Real number or real function, okay? And so it can be measured, okay? And so let's come back to our problem here, because we have to try to find now, we have this value for gamma, and now we want to find the value of the coefficients alpha and beta, okay? And using these findings, okay? So we have this function, okay? This is minus alpha k squared plus v0 will be equal to, this is the same number here, okay? Minus or plus I beta omega, depending on if gamma is equal to plus or minus I. And if we compare with our energy for a free particle, okay, we have kinetic energy plus constant potential energy equal to h bar omega, which is the total energy, okay? So if you compare these two, okay, expressions, you will see that you can see if alpha is equal to minus, okay, alpha here, minus alpha, which is the coefficient of k squared. What is the coefficient of k squared here? This is this one, okay? So minus alpha would be equal to h bar squared over 2m, okay? And in the same way here we have omega. What is the coefficient of omega? It is this one, and it would be equal to h bar, okay? And so here we will have minus or plus I beta equal to h bar, okay, which we can write as beta is equal to plus or minus I h bar, okay? And so we can choose, okay, it is not important, okay? Physically it's not important to choose one or the other. The convention is that we choose this plus one, okay? So everybody does that. We choose this plus one, and so we write now our equation with these two coefficients, minus alpha equal to this. So you have minus, this is alpha, okay, derivative, okay, of psi plus v psi equal to beta, which is I h r bar, and this is, okay, actually this is what could be a wave equation. Okay, we have verified that it works quite well with a free particle, and I won't get into the details and do it more rigorously. Okay, I will tell you this is the Schrödinger equation. Okay, so it doesn't work only for free particles. This would be V0 here. Okay, I already wrote it in the general way. Okay, it works for whatever potential energy phi of x and t you have in your problem. Okay, so this is the Schrödinger equation. This is the wave equation for matter waves. Okay, and so it was deduced, okay, by Schrödinger in 1926, and so as I said, it was deduced, okay, from free particle considerations. Okay, so very qualitative, but very physical also. So we have some good physical insight on how this wave equation works, and we have, okay, generalized it to any configuration of potential energy. Okay, and I said to you, okay, this is it. Okay, we won't get more rigorous. Okay, and also I have to say that it is a non-relativistic wave equation. Okay, for the matter waves. Okay, the relativistic equation was deduced by Dirac. Okay, a few years later in 1928. Okay, and to deduce these relativistic equations. Basically, we can say that the conditions were the same, but the expression of the energy was not the classical one we used. Okay, we used this is classical in the sense of the velocity. Okay, it is not classical, but it is quantum mechanics. Okay, classical in the sense that the velocity of the particle is much smaller than the velocity c. Okay, classical, we have the expression of the energy is p squared over 2m plus v. Okay, and so the relativistic equation is different. Okay, so we have our Schrödinger equation. We write it, this is Schrödinger. And so I wrote this one, okay. First exercise to do, okay, to manipulate this equation and the solutions of this wave equation. And so to verify that this equation, okay, is linear in the wave equation, okay, we can see it, okay, mathematically it is linear because you have a constant term times, this is a second order derivative, but it is, you have no power, okay, you have no power 2 or 3 or 0, okay, of this derivative. Here this is directly proportional to psi, and this is also the first order derivative, okay, in function of time, and it is no power 2 or 3 or, okay. So we can show that it is linear, and for that we have to show that this wave function, okay, which is a linear combination of psi1 and psi2. I said it, psi1 and psi2 are solutions of the wave equation. It means that, what does it mean that you say that say psi1 and psi2 are solution? It means that minus h bar square over 2m d2 of psi1 over dx2, okay, plus v psi1 equal to h bar I bar, okay. Okay, so this is a solution. I say this is a solution, so it obeys this equation. And same thing for psi2, okay, to psi1 over, okay. So this is what it means to say that there are solutions, okay. And when you want to show that this linear combination is also a solution, so what you have to show, this is the same thing, obviously, that T2 of psi over plus V psi is equal to A H bar. Okay, this is what it means. So this one and this one, you know it, and you have to show that if psi has this dependence on psi1 and psi2, it also is a function of the wave equation. Okay, so only to verify, to check that our wave equation is linear. Okay, and here I want to remember you also that we have this Born. I don't think I told this name last lecture, okay, but who gave this interpretation to the wave function is Born, okay. And so as I said, psi of x and t has no direct physical meaning, okay. It is a complex function, okay. But if you compute, okay, this quantity, okay, what is this quantity? You have p of x dx equal to psi of xt square. Okay, this is real. The x is the probability of finding the particle between x, okay, these two positions, x and x plus dx, okay. So this is the first use we have for this wave function. I can try to, I think we can already just a minute. I want to show you. So one of the things we can, I can already write it here. If you say that this is a probability, okay. So when you integrate here over space, okay, dx from minus infinity to plus infinity, you should find the probability of finding the particle, okay? Somewhere in the universe, okay? Between minus infinity and plus infinity. So it means that this value is 1, okay? This is 100%. Because if you have the wave function, okay, it is associated to a particle, an existing particle, okay? So what is the probability of finding this particle? It is, okay, if you look for it in the whole universe, you will find it. So the probability is 1, okay? So this is very useful. We will see, okay, to find some constant, okay, some constants in this wave function. And so let me see if I can do some example here. There are some very useful examples. No, this one I don't like it. So I will take here. This is an example I am taking from the iceberg book, okay. So at the end I will write it, okay, in the bibliography, okay. And so we have some examples here. Okay, so I have some. Okay, so this is a wave function. Okay, it has some. It is a function of x and of t, and this is actually okay. This is for example of the iceberg book. Okay, I'm going to write it here. This is from iceberg. So this wave function, okay, this is the wave function for the lowest energy state of a simple harmonic oscillator, okay? So what is the this lower state? So we have a harmonic oscillator. We have V of x and t, okay? It doesn't depend on time, okay? It is equal to something alpha. I won't call it alpha because I already used it. Okay, now this is an energy, epsilon zeta eta. Okay, I can call it A, okay? A constant time x square, okay? And so this is the harmonic oscillator. You know it from classical physics, okay? And so when you you solve, we are not going to solve this equation. I am only writing here that minus actually this okay. My wave function will be, oh no, this one is a function. Okay, this is the energy. Okay, so you will put here the x squared side. Okay, so you in your Schrodinger equation you put the form of this potential, okay, and so you will have this this solution here. And so I think this this example, I'm not going to treat this example, okay. It is to verify that it is a solution of this equation, okay. So you take it, you derive as a function of t, you derive twice as a function of x, and you show that it obeys this equation, okay. So what I'm going to do now is not proving that it is a solution. I will accept that it is a solution, and I'm going to find okay, the probability density. Okay, what is the probability density? This is the density. So in one dimension, okay, in one dimension, this is the probability of finding the particle between x, okay, and x plus dx divided by dx, okay. So it is this is p of x, okay. So this is the density, okay. So this is what is the unit of this probability, this density, if it is per meter, okay. And if it is 2D, okay, the density P of R, okay, will be in per square meter, and in 3D it will be P of R in per volume unit volume unit, okay. And so here we have one dimension, okay, and so we want to have some idea of what would this probability, this density be, okay. And so maybe I can, this is really a mathematical problem. I want to treat it, okay. To begin it, I think I will put it in a homework problem set, okay. And so you will have P of X, okay, which will be equal to the square modulus of, okay? And so you have to square, okay, this function. So this is, you have, oh, this will be very easy because you only have this complex part here in this phase term. So this will be equal to 1, okay? So this will be equal to, okay, square modulus of A, okay? A may be complex as well, okay? And so when you will, so here, this is exponential of -2, okay? Time blah, 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 okay? This coefficient, okay? This coefficient. And this is, what is the modulus of this one? This is 1 because exponential of minus E theta times the complex conjugate, okay, exponential of E theta, this is equal to 1, okay? So this will be equal to 1. So this is very easy to have an expression. And so you will show, so this is exponential of minus 2. Okay, you have no more these 2 because it was at the denominator, okay, h bar x square. H bar square, I think. No, h bar x square. Okay. And so what kind of function is that? You see that it is, this is a Gaussian function, okay? Exponential of minus constant times x squared. This is a Gaussian function centered at x equal 0, okay? So I'm going to copy and paste, okay, this. Okay, no, I won't do it here. Okay, so this is a Gaussian, okay. Gaussian probability. So you have something like P of X, and you have X here, 0, X, and so this is maximum here. So at X equal to 0, you will have 1 here, so you will have modulus of a square, okay, and you will have some decaying, okay. This is a Gaussian, okay, believe me. It's not very beautiful. So this is the probability, okay, you have some harmonic oscillator, okay, so you have discrete energy levels, okay, and so this is energy scale, energy, and so this is for example the position x, okay, and so I will write this quotient here. And so what do we have? What is the probability of finding the particle here or here? Okay, this is 0. Okay, these are the turning points, and so you have a higher probability of finding the particle right at the middle of, okay, of this extinction. Okay, so the particle is oscillating in this energy potential, this potential energy, okay, in this well. And so it can be at any position between these two turning points, okay, but the higher probability of finding it here right at the middle, what we call x equal to 0, okay. And how do I know that? It is because I have solved this Schrödinger equation, okay, and I have found, okay, that this solution has this probability density, okay. And so I'm going to stop here, okay, because I would need to have other slides to show you that what I want to show you here. We have no time to go into the details, okay, because this is our last lecture. What I want to show you here is that when you solve this equation, you find, okay, so what you do when you want to study a quantum mechanical particle, okay, you solve the Schrödinger equation for this particle, okay. And so solving the Schrödinger equation for the problem, okay, so the problem is what? It is the particle, okay, so the particle, what is, it is essentially the mass of the particle, okay, because you have minus h squared over 2m, okay, so you have to have the mass of the particle, and also this particle in the potential energy, okay, V, okay. So you put these two quantities in your equation, and you will find, okay, solving it means that you will find the wave function. And actually, it will mean that you will find something more interesting, okay. This is, you will find its energy, okay. You will find the wave function. And so what kind of information, okay, can you extract from this wave function? So you can extract the higher, the density, okay, the position density, okay, of the probability of finding your particle in some place in the space, okay. But it is not only that. You can find its energy, you can find its angular momentum, you can find okay, everything you want to know about the particle, okay, you can extract from the wave function, okay. And this is what I have no time here to show you. I will finish it in the next lecture, okay, that I will post on the YouTube channel, okay. It should be a short one because really we don't have, okay, it is not necessary to go into the details, okay, but to have some insight into what we can do with this equation and with the wave function we find, okay. So let me